This week we look at work, power, and later on friction. But let's focus on work and power. And probably the best way to conceptualize what energy is and ultimately what work and power is to consider where this energy comes from. And let's start by looking at the sun, because that is the source of most energy, as you're going to see, that we ultimately use on the planet. So coming in from the sun is 174 petawatts. Now a petawatt is 1 times 10 to the 15 watts. You can count how many zeros that is. It's a significant amount of energy. Okay, some of it is lost, reflected back to the atmosphere, etc. The bottom line is 89 petawatts is absorbed by the land and the oceans. And while we're on that, if we think about where power comes from, fossil fuels are also solar energy, so is wind energy, so is wave energy, so is hydro energy. The only energies that we deal with on a daily basis that are not from the sun are nuclear, tidal, and geothermal. The rest all ultimately come from the sun. So before we quantify exactly how much energy is in various activities that we do, we can take a look at a few snippets from a renewable energy slideshow that I present to better quantify these matters. So let's start relating this energy to a simple task of, in this case, lifting pockets of cement onto a truck. All of us have tried that at some point, I'm sure. Now, a pocket of cement has a mass of 50 kilograms, which is about 500 newtons of weight. Now, let's assume that we lift this pocket 1.5 meters from the ground onto a truck. And we recall from our school studies that work done is force times distance. So the work done per pocket, remember that was lifting the pocket, so exerting 500 newtons on the pocket and raising it through 1.5 meters would mean 750 joules of work was done in loading one pocket. So if we load 20 pockets, we would have expended 15,000 joules. And let's say that we did all of that in 10 minutes, which is 600 seconds. The rate of doing work would be 15,000 divided by 600, which is 25 joules each second. So that is the rate of doing work, also known as power, and also can be expressed in units with watts. Okay, so in other words, we are working at a rate of 25 watts. And of interest, a very fit cyclist can produce around about 220 watts for about an hour. So that's one way of quantifying that rate of doing work. Now let's look at this device. This is a prepaid meter, which in South Africa we use for purchasing prepaid electricity, and then we enter a number over here and it gives us so many units, as some people refer to it. Those units are in fact kilowatt hours. So let's have a quick look what a kilowatt hour is. What it means in simple terms is it's 1,000 watts or 1,000 joules per second for an hour. That is each unit that you buy. That's how much energy you're buying. So it is in fact 1 kilowatt hour, which is 1,000 joules per second, times 3,600. Remember that there are 3,600 seconds in an hour. So that is 36 with 1, 2, 3, 4, 5 zeros behind it, or in other words, 3.6 million joules. So 1 kilowatt hour is in fact 3.6 million joules. And in South Africa, we pay between R1.50 and maybe R2 per kilowatt hour. Let's leave it at R1.50 for the calculation, which would mean 2.4 million joules for a rand, or 0.0000416 cents per joule is the price we are paying. So let's go back to that previous truck example. Remember, we did 15,000 joules of work. So in money terms, to load that truck, if we multiply it by the price, our work was worth 0.625 South African cents. That can't be right. That really doesn't seem right. All that effort for 0.625 cents of energy. Well, let's look at it a different way. 25 watts for 10 minutes is 25 thousandths of a kilowatt. And it happened for 10 minutes, which is 1/6 of an hour. So let's divide it by 6. So we get 4.1666 times 10 to the minus 3 kilowatt hours. So let's multiply that by the rate of R1.50 per kilowatt hour. You can do that. And you'll see that you end up at the same value of 0.625 cents worth of energy. Now let's quantify all of this to the amount of energy that we use per day in a normal residential home. So a family of 4 living in a suburb in a South African city will more than likely use around about 30 kilowatt hours per day. Okay, so that works out to 45 rands worth of electricity per day. Now let's get that back to the truck example. If the energy was coming from our physical endeavors, we would have to load 7,200 trucks per day to make as much energy or expend as much energy as the amount used by a normal residential house in one day. So that's one way of tying up energy usage to the basics of the measurement of energy. Before we step off that, let's look at one last example. Let's pretend that you boil 2 cups of water, maybe to make 2 cups of tea. Let's see how much energy is involved. Remember, Q equals MC delta T. It's another formula you learned from school. Now, 2 cups of water is around about half a kilogram of mass of water. There's the specific heat capacity of water, 4,200 joules per kilogram Kelvin. And let's pretend we take the water from 20 degrees C to, let's say, or to 100 degrees C because it's going to boil. So that's an 80 Kelvin increase in temperature. So 168,000 joules is required to boil 2 cups of water. If we take it back to the truck example, that is the same as loading 11.2 trucks. Remember, with those pockets of cement. In money terms, using the calculation from the previous example, 6.98, call it 7 cents of electricity is used to boil 2 cups of water. Now let's look at some big numbers. If we look at all the energy used on the entire planet, the world energy consumption, and I'm not just talking electricity usage, all energy, that would include burning of fossil fuels for powering vehicles, aircraft, etc., etc. Well, that number would be 550 exajoules. 550 exajoules is the world energy consumption, made up of these different sources according to the colors. Now, if we work that back to kilowatt hours using our conversion of 3.6 million joules per kilowatt hour, you'll find that the world energy needs are 152 times 10 to the 12 kilowatt hours per annum. Now, most of that energy currently comes from coal and oil, although there are other providers. Now, hypothetically, would it be possible to get all of that energy from solar energy, from photovoltaic panels? Well, we know there's going to be many practical constraints to getting that right, but just for a bit of fun, let's see how many solar panels we would need to make this happen. Let's start by looking at a few sunny places in the world. Now have a look at the units here, kilowatt hours per square meter per annum. Now if you look at parts of Australia, about here would be around about 3,000 kilowatt hours per square meter per annum. That is the direct normal irradiation. That is the quantity of solar energy striking the Earth at that point. The sunniest place in the world, oddly enough, is in South America. Here we have an even higher value of solar insolation, albeit over quite a small area. In South Africa, closer to home, we have an excellent solar resource as well. And in this area here, we're also in the 2,800 plus kilowatt hour per square meter range. And other parts of Africa, like North Africa, are also pretty good. So talking of North Africa, this author suggested that if we were to cover that rectangle or square of 300 by 300 kilometers with solar panels, we would be able to power the entire world. So if we could do that and we ran power lines from there to all parts of the world, we would be able to power the entire planet. That really does sound bizarre, but let's do a little calculation and see if it is possible. And let's not just look at electricity needs, let's look at all energy requirements. If we go right back to the beginning, 152 times 10 to the 12 was the world energy requirement. Remember, that was per annum. Now if we divide that by 2,800, assuming that that is the solar irradiation for the part of North Africa that was mentioned earlier, it would mean that we need to cover that many square meters with our solar generating devices to get that much energy. Now a PV panel, a photovoltaic panel, can produce about 14% of, or convert 14% of that energy landing on the surface of the earth to electricity. They are 14% effective, basically. So if we factor the number with a further 0.14, we end up with a larger required area of 387755 times 10 to the 6 square meters. And if you work that out, it's roughly 622 by 622 kilometers, which is a lot of solar panels, but that would be enough to power the entire world, all energy requirements. Obviously totally impractical, because at night there would be no energy. But if you could potentially have another, maybe you could halve this and have the other half on the other side of the world, where it is in fact daytime whilst this lot is experiencing night, and you had an interlinking power line, just maybe it would be possible. But obviously there's many other constraints. But from a purely theoretical point of view, that is feasible. Let's revise some of the basics of power and work. Remember that power is the rate of doing work. So if we have work done divided by the time it took, then in linear terms, that work done could in fact be force times distance. If you apply a force through a certain distance, you are doing work. And if we look at that, we find that distance over time is in fact velocity. So especially when we talk about linear motion, we could say that force applied times velocity is in fact power. Let's look at number 2. A delivery van having a loaded mass of 1090 kilograms travels for 100 meters up an incline of 1 in 8. That simply means the incline rises 1 meter for each 8 meters you travel along it. If the total tractive resistance is 535 newtons, that is the total force holding the vehicle back, which would be made up of friction and aerodynamic drag, we must determine the work done by the engine. So here's our vehicle on the incline, and the incline, as we said, is 1 in 8. So if you look at sine of theta, rise would be 1 over the distance traveled along the incline of 8 meters. So our triangle would have 1 meter and 8 meters. There's our right angle triangle. So sine of theta would be 1 over 8. And remember that whenever you have a body on a slope, you can take weight, which would be straight down towards the center of the earth, and you can replace it with 2 components, one into the slope and one down the slope. Okay, now those 2 components would be down slope, which is this one here, and into the slope. Now your theta would be this angle here, and this one would be weight cos theta, or if you prefer, mg cos theta, and this one here would be mg sine theta. So the easy way to remember it is any object, be it a vehicle or a block or whatever that is on a slope, has weight broken up into 2 components, mg sine theta down slope and mg cos theta into the slope. In our case, we are summing forces along the slope, parallel to the slope. So mg sine theta is the one we're interested in. There is the m, there is g, and there is sine theta. That is the component of weight down slope. And remember, the vehicle was moving up the slope. There's our little motion arrowhead. So opposing that is the sum of all the friction and the drag, which was 535 newtons. The tractive force is a force felt by the vehicle where its wheels contact the road surface. So you can replace all of that with a single arrowhead pulling the vehicle up the hill at the road surface, and we call that TF. TF obviously standing for tractive force. So if we sum the forces parallel to the slope equal to 0, we have TF up the slope and these 2 down the slope. So there's TF up slope is equal to 535 plus mg sine theta. So it follows that TF must be 1871.6 newtons, the tractive force. Okay, how much work is done? Well, work done is 1871.6 times 100. Remember, the 100 meters was the distance traveled up the slope. So force times distance gives you work done in joules. So 187160 joules is the work done to take this vehicle 100 meters up this slope. Let's look next at number 15, which is a vehicle on a level road, no slope involved. So it's a motorcycle traveling along a level road at 162 kilometers per hour. Tractive resistances amount to 135 newtons. Determine the work done per second, which is power in other words, developed by the engine. So here's our biker traveling along the level road at 162 kilometers an hour, which by the way is 45 meters per second, just divide by 3.6. And everything is nicely in balance. There's 135 newtons of resistance, and our engine via the chain and sprockets etc. is driving the rear wheel. The rear wheel is contacting the road surface, and the vehicle as a whole feels a pull at the road surface, which we call tractive force. How much is that tractive force? Well, it must be equal and opposite to the resistance, so it's simply 135 newtons if you sum all the horizontal forces. How much power is involved? Well, we learnt a little while ago that force times velocity would give you power. So in our case, tractive force is what the engine is supplying, multiplied by velocity. 6075 watts is the amount of power this engine must produce to make all of this happen. Next, let's look at number 20. Here we have a lorry truck of mass 6 tons, and it's ascending an incline of 1 in 112. So once again, 1 meter rise for 112 meters traveled along the road. And this is happening at steady speed, so in other words, there's no acceleration involved. The tractive resistance is 70 newtons per ton. Now that might sound a bit strange, but it's just a way of expressing the amount of resistance per ton mass of the vehicle. It's suggesting that the more heavily loaded the vehicle is, the more the resistance would be. So let's just bear with that for now. 70 newtons per ton. Remember, the vehicle had 6 tons, so straight away if you multiply 70 by 6, you're going to have the resistance in newtons for the whole vehicle. Okay, they tell us the engine is developing 12.5 kilowatts. Determine the speed of the lorry. So there's our vehicle on the slope. Theta, remember you can get that by taking sine theta as being 1 unit of the triangle on that side and 112 along here. So there's our triangle, our right angle triangle with a right angle down here, 112. So we can find sine theta to be that over that. We'll use that in a moment. Back to the forces acting on the vehicle. 70 newtons per ton. There were 6 tons, so 420 newtons is the total resistance. That is the force opposing motion. Remember, motion is up the slope. It was ascending. This here is mg sine theta. Okay, remember that was the component of weight down the slope. We're not interested in the component of weight into the slope because we're only summing forces parallel to the slope. And TF is how much tractive force our engine is supplying to the vehicle via the drive shaft, etc. Ultimately, the wheel rolling on the road is ending up with a pulling force, a tractive force experienced by the vehicle parallel to the road surface where the wheels contact the road. So we only have 3 forces, 1 up and 2 down. If we sum those, 1 force up the slope is equal to the 2 down the slope, this one plus this one. It means that the tractive force must be 945.54 newtons. And once again, power is force times velocity. And we know that the power developed by the engine is 12.5 kilowatts. We now know what the force is. So the rate at which we're moving, velocity, must be 13.22 meters per second. Or once you've multiplied by 3.6, 47.59 kilometers per hour. And here's a very similar one, number 21, except it's a train. The drawbar pull of a 300-ton train is 28 kilonewtons. Tractive resistance, 45 newtons per ton of the mass. What is the steepest slope the train will ascend? So here's our train. We haven't drawn in the locomotive, just the trucks. which is what defines the train in this example. So there's all the trucks. To be able to pull them, you must apply a force to the drawbar of 28,000 newtons. Resistance is 45 newtons per ton. There were 300 of those, so it's 13,500 newtons of frictional and aerodynamic resistance. And that always opposes motion. Motion, as we know, is up the slope. Here's the big one, which is the component of weight. A train is a very heavy thing, so 300,000 kilograms of mass is mg sine theta. That is going to be a significant amount of force, which is the component of weight down the slope. If we sum the forces, we have 1 up and 2 down. There's the 1 up, and here are the 2 forces down the slope. So it follows that theta cannot be anything other than 0.2823 degrees. Okay, now the question asked for the slope expressed as 1 in something. So there's our 1. What is the something? Well, sine theta is that over that, and theta is 0.2823 degrees, we just worked out. So let's make this something z. It follows that z must be 203, so the gradient can be expressed as simply 1 in 203. 1 meter risen for 203 meters traveled. Now try number 23 on your own.